Hello, let's begin with section 3.4. If you look in your notes, it says we're going to review examples 1 through 4 in your book. So this is on page 221 in your book. Examples 1 and 2 are tied together, so I will look at those examples together. Okay. So it says a store can sell 20 bicycles a week at a price of $400 each. The manager estimates that for each $10 price reduction, she can sell 2 more bicycles per week. The bicycles cost the store $200 each. X stands for the number of $10 price reductions. Express the price P and the quantity Q as functions of X. So first thing you always want to do for any problem is write down what you're letting X equal. What is your variable? Here they tell us, but in other problems they won't tell us. So X is the number of $10 price reductions. And then I need to find the price, right? So let's look at X. Let's make a little table. And let's look at price. Okay. So if she doesn't give any reductions at all, then the price of the bike, the manager estimates, so a store can sell 20 bicycles per week at a price of $400 each. Right? So that's the original price. If she offers one $10 price reduction, then the new price will be, let me write this in. It'll be 400 minus a $10 price reduction, which will be $390. Right? If she gives 2 price reductions, then you take 400 minus 2 of those, like $10 coupons. Think about it. Think about it like that. So that'll be $380. Right? So now if my price is X, then it's 400 minus 10x. Okay. So that is your price P. Okay. So P of X is equal to 400 minus 10x. Let's look at quantity. So if she sells, so it says at the beginning that she can sell 20 bicycles a week. So if she doesn't offer any kind of price reduction, she'll sell 20 a week. If she offers one price reduction, it says the manager estimates that for each $10 price reduction, she can sell 2 more bikes per week. So that's 20 plus 2, right? So that gives me 22. If she offers 2 price reductions, or 2 $10 coupons, then she can sell 4 more bikes, right? If she offers, so this would be times 1. If she offers 3, then she can sell 6 more bikes, so that's 2 times 3. Right? For each $10 price reduction, she can sell 2 more bikes. So if your price reduction is X, that's 20 plus 2X. So that is our quantity, okay? So in the past we've done problems where quantity was X. X is the number of bikes to sell. Here your quantity is not X. Your quantity is 20 plus 2X because X stands for the number of $10 coupons, number of $10 price reductions. Alright, and then it says use the information example 3, find the price and the quantity that maximize profit, also find the maximum profit. Okay, so let us look at that. So we want to maximize profit. Remember, profit is capital P of X. That's your, so profit is your price times quantity. Remember, that gives you our revenue, the money we have coming in, minus the cost. Okay, this is again revenue minus cost. Okay. So price times quantity, we know, I'm going to need some more space for this. Let me mark it here. So capital P of X. Price is 400 minus 10x. Quantity is 20 plus 2x minus the cost. Let's look at our cost. So the bicycles cost the store $200 each. And it doesn't mention anything about fixed cost. So what is cost? Cost is your unit cost times quantity. Okay. And then plus some fixed cost if you have fixed costs. Here there's no fixed cost, so it's just $200 per bike that it costs the store. And it's not going to be 200x, it's 200 times the quantity. The quantity is 20 plus 2x. Okay, so now we can simplify this whole expression. So we get 4 times 2, which is 8, and 3 zeros, and then plus 800x. So I'm just foiling these two, minus 200x, minus 20x. Okay, and then minus 4,000 minus 400x. Okay, so then when we simplify all of this all together, we get 8,000, and there should be an x squared somewhere. Hold on. Should be 10x times 2x is 20x squared. Whoops, sorry. Alright, so by doing enough of these problems, I know they should be quadratic. So let's see, minus 20x squared, and then we have 800 minus 200 is 600, minus 400 is 200x, and then 8,000 minus 4,000 is plus 4,000. So that is our cost, or that is our profit function, rather. Now we want to maximize, and you don't have to simplify this, you don't have to like factor out anything, because we're going to take the derivative anyway. Remember how we maximize? Take the derivative, set it equal to 0. So the derivative of this is going to be minus 40x plus 200, and you set that equal to 0, and then we subtract 200 from both sides, divide by negative 40, so we get x equals 5. So x equals 5, that is the number of $10 price reductions. So it says find the price and quantity. So the price, so that means she needs to offer 5 $10 price reductions. Or she needs to reduce the price by $50. Okay, so let's plug this into the price function. She started off selling each bike at 400, and then she's going to offer 5 $10 price reductions. This is coming from up here, which is 400 minus 10x at the top. Okay, and so that is going to be $350 per bike. The quantity she will sell is 20 plus 2x, so that's 20 plus 2 times 5, which is 30 bikes. So she can estimate that she'll sell 30 bikes at $350 a bike. And then what is the maximum profit? Capital P of x. Okay, so we're plugging, our profit function is right here, so that's minus 20x squared, which is 5 squared, plus 200 times 5 plus 4,000. Okay, so what does that give me? 5 squared is 25 times 20. Whoops. Oh Lord, hold on one second. Let me erase this. Okay, so 5 squared is 25, times 2 is 50, and then another 0, plus 1,000, plus 4,000, 5,000, so that's 4,500. So 4,500 is the max profit, okay? So here's the price, here's the quantity, and here's the max profit. Okay. So all of these problems are pretty much like this. Let's go on to the next problem. Alright, this is example 3. So we just did examples 1 and 2 together. Let's look at example 3. So you have an orange grower. He finds that if he plants 80 orange trees per acre, each tree will yield 60 bushels of oranges. He estimates that for each additional tree that he plants per acre, the yield of each tree will decrease by 2 bushels. How many trees should he plant per acre to maximize his harvest? Alright, first thing you always want to do is write down what your variable is, right? So x, it says for each, he estimates that for each additional tree that he plants per acre. So let x be the number of additional trees per acre. Okay. And how many trees should he plant per acre? If he plants 80 orange trees per acre, each tree will yield 60 bushels of oranges. But for each additional tree, the yield of each tree will decrease by 2 bushels. Okay, and we want to maximize our harvest. So harvest means how many oranges you have, right? So you have to look at the number of trees that you have. So harvest equals trees per acre. How many trees do you have per acre, and then how much do you get off of each tree? So the yield per tree. That'll give you how many total oranges you have, right? So let's find out how many trees he'll have per acre. So the number of trees, and let's make a little chart here. So he starts off with how many orange trees? If he doesn't add any additional trees, he starts off with 80. If he plants 1 additional tree, then he has 81. 2, 82. X, it's just 80 plus however many I added, right? 80 plus X. And then his yield, so if he starts off with planting 0 additional trees, each tree will yield 60 bushels of oranges. If he plants 1 additional tree, it says for each additional tree, the yield of each tree will decrease by 2 bushels. So it'll go 60 minus the 2, which will be 58. Right? If he plants 2, it'll be 60 minus 4, which will be 56. Right? If he plants 3, it'll be 60 minus 3, or 2 times 3, which is 6, so that's 54. So if he plants X number of trees, it's 60 minus 2X. That is the yield. So now we can put all this together and look at our harvest. So we want to maximize the harvest. Let me just call that H of X, capital H of X, is the number of trees per acre. So that's 80 plus X. Right, that's the, and the yield per tree is 60 minus 2X. Alright, and then we can simplify this. So 8 times 6 is 48, and we get 2 zeros. Minus 8 times 2 is 16, so that's 160x, plus 60x, minus 2x squared. So this gives me 4800 minus 100x minus 2x squared. And I want to maximize this function. Ooh, one thing I forgot to do. Ooh, let me go back before I forget. We did this before when we did optimization, other problems, right? So I'm sorry, let me just go back for 1 second. Actually, let me continue with this problem. Let's do this. Let's continue with this problem since we're on this problem, and then I'll go back to that one. So when we want to maximize, we want to take the derivative and set it equal to 0, right? So what is the derivative of this? Minus 100 minus 4x, right? We set that equal to 0. And you add 4x to both sides, and then you divide by 4, so you get negative 25 equals x. So how can x be negative? Well, if x is the number of additional trees per acre, then negative 25 means he should plant 25 less trees. So he should plant 25 fewer trees per acre. Okay, so he needs to plant, how many trees should he plant per acre to maximize his harvest? So we started off at 80 trees, so this guy needs to plant 80 minus 25, which is 55 trees per acre. Okay. Alright, now the one thing I forgot to tell you is take the second derivative. Before you even go on and finish the problem, take the second derivative. Because remember, the procedure for maximizing and minimizing is the same, right? You take the derivative and set it equal to 0. So you want to check that you're actually maximizing the harvest and not minimizing the harvest. Okay? So let's take the second derivative here. The second derivative is negative 4. Negative, when your second derivative is negative, that means your graph is concave down, which means we have a max. So that's good. So we are indeed maximizing. Okay? Let's go back to this problem and look at the second derivative here. So my first derivative is this. My second derivative, so my second derivative is from here, negative 40, which is again concave down, and we are indeed maximizing. Okay. If, for example, you got a positive number here, that means it's concave up, that means it's minimizing, which would mean you would not be able to maximize profit. You would actually be minimizing it, right? Which would be a bad thing. So you always want to do this check to make sure you're doing what you intend to do. Okay. Let's look at the last problem. Example 4. So you have a moving company. They wish to design an open top box with a square base. The volume is exactly 32 cubic feet. Find the dimensions of the box requiring the least amount of materials. Okay, so first thing when I see like a problem like this geometrically, I want to draw a little picture. Okay, so here's my box, and okay, there's my crooked looking box. Just pretend it's straight, okay? And it says open top box, so there's no top, and square base. So if it's a square base, then I'm going to call each side of it x, right? Each side will be the same. The volume is exactly 32 cubic feet. Find the dimensions of the box requiring the least amount of materials. Alright, so we have x, which is the base, and then we don't know how tall the height is, right? That's kind of what I need to find, is the base and the height. The volume, so how would you find the volume of a box? So the volume is going to be length times width times height, right? And that's equal to 32. So from there I get x times h is equal to 32. So that's x squared h is equal to 32. So now I can solve for h and get 32 over x squared. Okay. So instead of writing h, I'm putting everything in terms of x. So now I can write the height as 32 over x squared. Okay, and this again is the height. Alright, and then it says find the dimensions of the box requiring the least amount of materials. So I want to require the least amount of material. So that's the surface area. So we want to minimize the surface area. Okay, let's call that capital. Let's just call that A for area. Okay. So what is the surface area of the box? Well, you have the base, right? So let me change the color. You have the base of the box. What's the area of the base? So that's squared. And then you have the side of a box, right? So let's, for example, look at this side. So that's x times, so that's going to be x right here, x times 32 over x squared, right? And we have, how many of the sides do we have? We have 4 sides. So there's 4 of them, right? And there's no top, so we don't have to worry about the top. So when we do this, we get 4 times 32, which is 128, divided by x, okay? So that is going to be the area of all the sides together, okay? So this is going to be our function for surface area, and we want to minimize this function. And notice how I've written it in terms of x. Okay. So this is a of x. So we're only solving problems with one variable here. Now we want to minimize. How do we minimize? You take the derivative and set it equal to 0. So this I'm going to rewrite to make the derivative taking easier. X squared plus 128 x to the negative 1. So then this becomes 2x minus 128 x to the negative 2, which is 2x minus 128 over x squared. So I'm going to set that equal to 0. Okay. And we move this over to the other side. 2x equals 128 over x squared. And then I want to multiply both sides by x squared and divide by 2. So then this gives me x cubed equals 128 divided by 2 is 64. And 4 times 4 is 16 times 4 is 64, so x equals 64. Okay. Notice how to maximize or minimize, we need to find the critical numbers. Right. The critical numbers is where the derivative is equal to 0 or undefined. The value that makes the derivative undefined here is x equals 0, right? So here x equals 0 will make the value undefined, but we cannot have a box with 0 width or 0 length. So that's not a viable option, okay? But I want you to recognize that that is still a critical number, okay? Oh, and I shouldn't say x equals 64 here, my mistake. X equals 4, okay? So, yeah, 4 times 4 is 16 times 4 is 64. So x equals 4 is our base, our length of the base, length of the side of the base. Let's take the second derivative here. Okay. So where's my first derivative? Right here. Second derivative is 2, or from here rather, let me do it from here. 2 minus, what is that? 100 or 256. X to the negative 3, okay? But once I plug 4 into here, right, this is 2 minus 256 over x cubed. Once you plug 4 into here, which was our critical number, we get 2 minus 256 over 64, which is going to be a negative number. That's concave. Is that right? Let me think. I think I made an error here, because I should be minimizing, not maximizing. So let's see. Oh, when I pull the negative out front, this becomes positive. So that's my error. Whoops, sorry. Positive. Positive. So this is actually greater than 0, which is nice. because I'm greater than 0 means it's concave up, which means we're indeed minimizing. Okay, so that's the way you can check, right? And then double check, and if it turns out you're actually maximizing, then maybe there's no way to minimize. Okay, so x equals 4 is our side of the base. So then what's our height? So height was 32 over x squared, which is 32 over 4 squared, which is 16. So that gives me 2. Okay. So the base of the box, or the what do we call the dimensions of the box, is going to be 4 by 4 by 2. So that's our length, that's our width, and that's our height. Okay. So this box I've drawn is a little bit tall, right? It's actually going to look like so that'll still give us a volume of 32. 4 times 4 is 16, times 2 is 32, but it'll minimize the amount of materials that we need. Okay. Alright, so those are the examples in your book. Your homework problems will be similar to these, where you have to maximize or minimize some quantity. Okay. So you always want to start off with, what information is given, what are you trying to minimize, and write that in terms of one variable. So if you have any questions, please get in touch with me via Blackboard or email, and I will be happy to answer your questions. Okay, thank you for watching.